Welcome, this is the AP Physics Workbook solution. We are on Unit 3, Circular Motion and Gravitation. The section is 3.I, which is on the conical pendulum. Here's the scenario. Consider a ball of mass M is connected to a string of length L. A student holding the free end of the string while hurling the ball in a horizontal circle with a constant speed. The angle between the string and the vertical is theta. The student assumed to whirl the ball faster and faster in order to make the string become horizontal. No matter how fast the student whirls the ball, the string will never become horizontal. All right. So first of all, the dots below represents the ball at the instant it appears in the diagram. Draw a free body diagram showing and labeling all the forces. Okay. So what I have here on the right hand side is a conceptual problem from your textbook talking about a tether ball. Okay. A tether ball behaves the same way because there's a rope being tied and the ball is being swung horizontally. All right, and here are the forces. If you take a look, here you could see that direction of the volleyball. Okay, what is pointing in towards the center of the pole is going to be the force of the tangential, but that is in the x direction. Okay, going straight up is the force tangent vertical. What is going down is force of gravity, mg, and what is going diagonally is the regular force of tension. What you have on up and to the right is your components, okay? So it's done the same exact way, all right? If you would like some more information, just read this. Those are the notes. All right, moving forward. All right, so what are we going to do here is using this diagram, we are going to draw the forces, but not the components, okay? Remember the F ten, ten the F ten the tension force in the y and the tension force in the x are components, okay? So here there are only two parts. Here we have the force of gravity going down. Now that's pink. That should be red. Okay. Let's see. 1, 2, 3, 4, 5, 6. And here, this is diagonal. 1, 2, 3, 4. All right. And what was going down is force gravity. Here's force tension. All right. Good. All right. So, by discussing a specific feature of your force diagram, explain why the rope cannot be completely horizontal no matter how fast the ball swirl. Okay. So, a couple of things that you should notice. All right. Think about, they said here, why should it be complete? Why is it impossible for the force of tension to be completely horizontal? All right. So let me just take out all the lines here and we can just write it. Okay. All right. So there is the force of, so there is the force due to gravity that is always pulling the rope down in the vertical direction, right? Okay, right? Because as you keep swinging, as you increase the spinning speed of the ball, okay? All right, that's you swirling it faster and faster and faster and faster and faster. The horizontal part of the tension will increase. Okay. All right. But there always exists, right? The horizontal part of the tension will increase, right? Easily, that's wrong, easily, because there is no force fighting against it in the horizontal direction. Okay, but that should be in the, because again, there's no force fighting the horizontal part. The vertical part will always have the force of gravity going against it. It will be super, super impossible unless you like go off of the, unless you weaken the force of gravity, right? That's the only way you, if you weaken the force of gravity, you could sort of get it up, right? Because there's that vertical part of force of gravity that's pulling up against it. Okay, so this is a quick explanation, but the math here works much better. Okay, so here you're going to derive an equation that relates the speed of the ball to the circle of the length L and the angle theta. All right. Okay, this is a long deviation. Okay, very long deviation. But in your textbook, you should have this problem. All right, in the Kagushi book. All right, you should have this. Right, this is a car that is being banked on a road. Okay, so the force normal isn't straight vertically, it's on an angle. So there's an F force normal sine and a force normal cosine. All right, but notice it behaves the same exact way. You're going to set up Newton's second law. You could pause it here to get a better understanding of how I'm going to set up the deviation for the workbook. Okay, good? Because I'm going to do the same exact way. All right, okay, so we start first here with Newton's second law. Right? You are going to see this version in the formula sheet. You're going to multiply this by m, multiply this by m. You're going to get am is equal to delta f. Right? Am, or mass times acceleration, you might see mass times acceleration, is equal to the summation of f. Or you're going to see, because sometimes they like the summation of f on the left hand side, and the MA is on the right. So you're going to see this version. Okay? All right. So let me, again, that's just basic stuff. So I'm going to clean this up and start with this line. You should know where I got this. All right? So the summation of the F is equal to the mass times the acceleration of the system. All right. So, okay. You want to here only look at the vertical part. So the vertical part, why? Because right here they notice the y in the acceleration in the y direction. Okay, this is going to be here 0. Right? Very beautiful in that sense. Okay. All right. So the two parts that are in the y direction is the cosine part, because that's up and down, and the force of gravity. So we rewrite in it same exactly like this one. Okay, so but here it's not force normal, it's a rope, so it's force tension. Force tension cosine theta minus mg is equal to mass times the y acceleration. Okay, exactly like this is done. Right, and you could say since there's no vertical motion, right? There's no acceleration in the for the system in the y direction. We can set it equal to 0. Right, so the right hand side is going to be equal to 0. Ft cosine theta minus mg is going to be equal to 0. Okay. Now here our goal was to um, get it in terms of v, l, and theta. So I'm going to rewrite it exactly the way this is. Okay. So here I'm going to move over the mg. So ft cosine theta is equal to mg. Divide by cosine theta. Ft is equal to mg cosine theta. All right. Good. Okay. So, all right. Now, what you have here is, you see how they stop here? Now you want to do the force normal into the equation for the horizontal motion. All right, so I stop this. Okay. Now I'm gonna do the the x component. All right. Good. Now the part that made this up is what? F t sine theta minus ma x is equal to ma right here. X, this goes to 0. Okay. Brings this over to the right. Okay. You should have summation of, sorry, you should have f t sine theta is equal to max, right? Because this became 0, right? Sorry, ax, so this becomes 0. Okay, the ax, right, it's a centrifugal acceleration, becomes mv squared over r. Sorry, becomes v squared over r. So this is ft sine theta is equal to m v squared over r. All right. So now you have to make some more adjustments here. Okay, so we need to know, right, what f of t is, but we do know what f of t is. Okay, this is the whole reason why we set this one up. Okay, this f of t can be substituted back here. So this was the substitution, mg cosine theta, right? Okay, and the rest is the same. So that was the substitution for ft. Everything else is going to remain the same. Boom. There it is. All right. But you should know what sine and this is some trig here. All right. Okay. So the fact that sine and cosine are right here, okay, you need to understand that, okay, the definition, tan theta is defined as sine theta over cosine theta. All right. So what you have here is going to be mg tan theta is equal to m v squared over r. The m's are going to cancel out. Okay. Good. All right. So you should have here g tan theta is equal to v squared over r. You have to understand this substitution, that r, which is the radius, is defined as, this is actually given to you, is equal to the L sine theta. So this can go in right there. Make that substitution. So it should look like this as the next step. Boom, boom. L sine theta. Good. Multiply this over to the other side. You should now get LGL tan theta sine theta is equal to v squared. Again, the order doesn't matter, right? You could have sine theta, tan theta. Doesn't matter. V squared. Okay, v is going to be equal to the square root. So GL tan theta sine theta, the square root of that. There you go. That is the velocity. Okay. Again, a lot of steps, a lot of substitutions need to occur, okay? You need to understand that to even do this, you have to set up two equations, all right? It's a system, basically. And you're going to do substitution here. Then after substitution, you're just going to make a different, you're going to need your, so here, this math that occurred here was using, this is substitution in systems of equations. All right, this is from Algebra 1. Okay, you need to know this skill right here. That's what occurred. Then from here, this was a trig ratio. Okay, you need to know your trig ratio from geometry or IM3. Then here, this is what you learn. This is from physics. Okay, this is from physics. This is in the formula sheet. All right, the r, the radius, is equal to the L sine theta, right? That's the length times theta, okay? And there you go. That's how it should look like, all right? Okay. All right, good, good, good. All right, so lastly, how does your equation in part B show that the rope cannot be horizontal no matter what? All right, so, okay. Show that cannot become horizontal. So let's just look at what horizontal is, okay? Horizontal will look like something like this. Here's the ball, here's the rope, here's the horizontal, right? And the theta here is equal to 0, right? Good? Okay. Okay. Does that make sense? Wait, hold on. Show when the rope cannot become horizontal, if theta, how is the ball in part B showing the rope cannot be horizontally no matter what? Is that, hold on, let me see. What do they mean by horizontal? Does that mean when it's 90 degrees? No, this is when it means oh, okay. This is what they're referring to. So they want the rope, right? They want the rope to be completely horizontal here. So they want this angle here to be to be 90 degrees. That's what they mean. Okay? So the question is this, right? First of all, what is sine of 90 degrees? Okay? Sine of 90 degrees is just 1. Right? So this is fine. But what is tan of 90 degrees? All right? That's the issue. So I just grabbed a calculator to sort of show you. Hopefully this is in radians. So sine of 90 degrees is equal to 1. Perfect. What is tan of 90 degrees? Undefined. So technically, the fact that tan of theta is basically undefined, it wouldn't work. Okay? This basically, so let's do tan of, before we even reach that. You see? Do you see how he keeps getting bigger, 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 bigger? Right? So if it's 89, it's this big, right? It's 57 degrees. But if it's 89.9, it's that. Do you see? As I approach, if you take the limit of theta approaches 9 degrees, look at how the fact that I keep adding nines to the end of the decimal, it approaches 0. It approaches 90 degrees closer. Watch as how the number gets bigger, bigger to the point that it's infinity. So you would say here that it is impossible to have a unlimited velocity. It's impossible to have an unlimited velocity due to the tangent value. The tangent value approaches undefined values. Right? It approaches infinity. Okay, it approaches infinity if you want to think about this in terms of calc. The tangent value approaches infinity as the angle approaches 90 degrees. There you go. And at 90 degrees, it's considered undefined. There you go. All right. Okay. Those are all your solutions. The hard part is working through this whole deviation, right? Again, systems, trig ratio, formula sheet, barely in the end. Okay, this is a neat way of looking at it. All right, understand that the tangent theta here will give you your velocity over your radius times gravity. Sometimes this is a very easy formula to work with. Okay, but here you go. If you would like to take a look at this problem, all right, which is really good to take a look at. Okay, let me just zoom it in for you so you could see it better. Right? It's for a car traveling around a circular radius r. Determine the formula in which the angle in which the road should be banked. The fact that you could bank the road, there is no friction required to keep the car on the road. All right? Good. This is the same reason why racetrack will have bank angles, is because cars can lose traction, so their coefficient of friction can like almost go smaller and smaller. But the fact that you have a banking, it helps it. All right, there you go.